Okay, right, so let's continue. We're now considering the equation x composed with x is equal to 2. So if we look at our Cayley table up here, the solutions are pretty obvious. We can do it by brute force. So we can take, because this group is so simple, it's only got 4 elements. So 0 composed with 0 is equal to 0, so 0 doesn't satisfy this equation. 1 composed with 1 is equal to 2, so 1 does satisfy this equation. So x is equal to 1 is a solution to this equation. 2 composed with 2 is equal to 0, so that's not a solution of this equation. And 3 composed with 3 is equal to 2, so 3 is a solution. So the two solutions are x equals 1 and x equals 3. So we have our two solutions. Now what we want to ask is there a link? Is there a transformation that we can do that will, if we know one solution, we can get the other one? And that's the basis of Galois theory. So we're going to try and find this transformation. So we'll call this transformation phi, that's going to map 1 into 3. We don't know, of course, that it's going to map 1 into 3. We're trying to find a composition that will be able to, if we know one solution, then necessarily the thing that this maps that's root onto will also be a root. So what we're going to look at is, if we take this equation, x composed with x is equal to 2, and we take this transformation on both sides, so it'll be phi of 2, then what we need to happen is we need phi of x composed with phi of x to equal 2, don't we? Because that's what we want. That's what we want. We want if x is a solution to this equation, we want phi of x to be a solution to this equation, and clearly phi of x needs to satisfy this equation thus. But if we act phi on this equation that we know to be true, then we know firstly that phi of 2, if you map phi of 2, phi of 2 has to be mapped onto 2. So I don't think I'm doing a very good job of explaining this. Right, so I'm going to tell you outrightly what this transformation is. It's a group automorphism. What we need is what is a group automorphism? We'll just revise what a group automorphism is, because if we revise that, we'll see why it obeys this property here. So a group automorphism is a set automorphism. First, it's an automorphism of the underlying set of the group, so this set here. And the set automorphism, remember, is just a mapping of the set onto itself. So you draw another set here, and you map each element onto another element on this set. So 0 could go to 3, 0 could go to 2, 1 could go to 3, 2 could go to 1, and 3 could go to 0. That's a set automorphism. It's a mapping of the set onto itself, where each element goes to another element in the set. A group automorphism is a set automorphism, but it also has to play nicely with this composition here. Specifically, if you have two elements in the underlying group, in the sets that underlies the group, and you compose them together using this composition, and then whatever that value is, so we compose A and B and get a new value, say, then if you transform this, and phi represents this function, it will, so A composed with B is some new element of the group, because obviously a group is closed under composition. So you take two elements in the group, you compose them together, you get a third element, and you transform that third element using the set automorphism, and that has to equal it has to equal the first element mapped into onto a new element in the set, and then composed with the same composition, because it's the same set, remember, that it's the same set, so you can still use the same composition. But that's the condition for it to be a group automorphism. That's actually the condition for it to be a homomorphism. But since it's a set automorphism, if it satisfies this property as well, it's called a group automorphism. Okay, so because our function phi, our group automorphism, satisfies this property, we can then, if we know x composed with x is equal to 2, okay? If we act phi on this, phi of x composed with x is equal to phi of 2. So what we're just doing there is x composed with x is some element in the set. It's actually the element 2. But because this law holds true, we can compose, because this is truly equal to this side, we can map this thing onto its new element in the set, and we can map this thing onto its new element in the set, and the relation is still true because they're the same thing. But because this is x composed with x, we can split this up in this way. So phi of x composed with phi of x, and it has to equal phi of 2. That's what we know from it being a group automorphism. But now we want... Oh, sorry, you can't see this. But now we want it also to satisfy this old equation. So phi of x is still an element of the set. It's no longer x potentially, but it's still an element of that same set. So if this was 2, then then phi of x would satisfy this equation, as it would satisfy the equation 2. So what we're going to demand is that phi of 2 is also equal to 2. So we have got a pretty steep order here. We want a group automorphism that happens to map 2 onto itself. And in the next video, I will show you the group automorphism that does that.